Hello, greetings from Dr. Sadiq Ali. I want to actually solve some examples. So here let W, that is a set, and it is a collection of all sequences, E1, E2, the nth term of the sequence is an, and so on. So this is an infinite sequence of real numbers such that that sequence must be converges to 0. So here limit as n tends to infinity of the nth term of the sequence must be 0. This is our collection. And we want to show that this is a subspace of, to show that this W is subspace, subspace of vector space V. Here vector space V means vector space of all the infinite sequences, and among all the infinite sequences here in W I have collected only those sequences which are converges to 0. It means that those sequences whose limit of nth term must be 0. So that's why W is a clear-cut subset of V. And now only we have to check that whether it is a subspace or not. So now our target is to show that this W is a subspace. So tell me, to show the subspace, what we need and what we have to declare that so that it become subspace. And the thing is that that set want to become a subspace, that must be a subset of V. So clearly V is a collection of all the sequences. Here also collection of sequences. The only particular sequences we have collected here whose limit of nth term is 0. Therefore clearly we can say that clearly W is a subset of V. Now the second thing is claim to show that W is a subspace of V. Subspace of V. Now how we can show that? For that you need two elements on the W. So I'm denoting these two elements by X and Y. You may take any letters, but here I am considering X and Y, the members of W, and check the linearity, we need two scalars, so alpha beta belongs to F. Okay. Now what is our claim? Our claim is to show that the combination of these two elements and these two scalars like alpha x plus beta y must be a member of W. So how I can show that? So here X is a member of W. It means that all the elements of W are infinite sequences. So that element I am denoting by X. It means that X is a name of one particular sequence which is coming from W. So here X is coming from, you may write here since X is a member of W, therefore X can be written as A1, E2, nth term should be An, and so on. And one more condition in W, that is limit as n tends to infinity of An is equal to 0. Similarly, Y is also belongs to W. This implies that Y is again an infinite sequence. So we can denote it by B1, B2, and nth term should be Bn, and so on. And also this sequence must converges to 0. That means limit as n tends to infinity of nth term, that is Bn is equal to 0. Let me call this these two limits as an equation number 1. Okay. Now, I want to show that alpha x plus beta y is a member of W. That is to show that uh, alpha x plus beta y is a sequence, infinite sequence is a sequence, and also we have to show that limit as n tends to infinity of nth term of alpha x plus beta y, that is denoted by suppose Sn, must be 0. Okay, so how I can create a sequence alpha x plus beta y by using two sequences x and y. So alpha x plus beta y can be written as alpha, and what is x? Tell me. A1, A2, nth term an, and so on, plus beta e into b1, b2 up to bn, and so on. So after multiplying this scalar to all the terms of the sequences, I'll get another sequence, that is a scaling sequence. Alpha a1, that would be the first term, alpha a2, that would be the second term, and what should be the nth term? Tell me. Alpha an. Okay, and so on. Plus, if you multiply by beta to this second sequence, then again beta b1, that would be the first term, beta b2, that would be the second term, in this way beta bn, and so on. Okay, now how to add two sequences? So addition of two sequences is again a sequence, and there should be term-wise addition. So first term of the first sequence plus first term of the second sequence, and this addition will become a first member of new sequence. Okay, so alpha a2 plus beta b2, this will be the second term of the new sequence. In this fashion, the nth term would be alpha an plus beta bn, and so on. So clearly, alpha x plus beta y is again a sequence. Now, one more condition we have to show, that is the limit of nth term. Now, what we want to show, that to become a member of W, limit of nth term must be 0. So I am considering limit as n tends to infinity. What would be the nth term of this new sequence? That is alpha an plus beta bn. Limit is having linearity property, therefore we can find separate limit of each term, and therefore we can write alpha into limit as n tends to infinity of an plus beta into limit as n tends to infinity of bn. And from the equation 1, already we have written here that the limits are 0. Therefore, using equation number 1, it can be written as alpha into 0 plus beta into 0, and we know that alpha into 0 is 0, and the total summation is 0. So we have proved that alpha x plus beta y is an infinite sequence, as well as we have proved that limit of its nth term is 0, and because of these conditions, alpha x plus beta y will become a member of W, and hence W and elements of W satisfied condition of subspace. Therefore, now we can say that W is a subspace of V. Now, let us take one more example. That is, I'm writing the example first, then I will explain. The problem is if f is a field of real numbers, show that the set of real valued continuous functions on the closed interval 0 to 1 unit interval forms a vector space over F. Now, this is a question of vector space, not subspace. All right. Keep in mind, don't be confused that to show vector space, we have to show all 9 conditions. And to show subspace, we need only one condition. So therefore, here the question is related to show vector space. Therefore, we have to prove all the 9 conditions required for vector space. So if I'm suppose giving a name to such a set which containing real valued continuous functions, so that name I am giving suppose V. All right, V is functions denoted by F, so that F is continuous real valued on unit interval 0 to 1. And we have to show that this set will create a vector space for the field of real numbers denoted by F, capital F. Now, how we can prove this? We know that to show vector space, we need 2 binary operations. One is addition, usual addition, and second is scalar multiplication. So, first of all, I want to prove that this V is an abelian group with respect to addition. And to prove the abelian group, we need 5 conditions: closure property, associative law, existence of the identity, existence of the inverse, and commutative law with respect to addition. So let us consider that F1, F2, F3 are members of V. It means that F1, F2, F3 all are continuous real valued functions on the closed interval 0 to 1, because they are coming from a set V, and V is a full collection of such a mappings. Now the number 1 is closure property. How we can show it? So we know that the addition of 2 continuous functions is again a continuous function on the same domain. Here the domain of F1, F2 is that unit interval, and therefore if we add these F1 and F2, its domain is also unit interval. And we know that the summation of 2 continuous functions is again a continuous function, and therefore F1 plus F2 will become continuous real valued function on the unit interval. Therefore it belongs to V, and therefore closure property satisfied. Number 2, associative law. That means F1 plus F2 is equal to F1 plus F2 plus F3. Sorry, here F2 and here it is F3. Because we can easily give the reason, that is associative law always hold in continuous mappings. Therefore, this associative law holds with respect to addition here also. Number 3, existence of identity. Now, what should be the identity? Identity is a zero mapping. So if that zero mapping is denoted by E, and it is zero mapping means E of x is identically 0 for all x belongs to unit interval 0 to 1. And look at this is a zero function. Zero function is always continuous, and therefore this zero function is a member of V. And if you add any f1 plus this E, and if you act on any element x, then it is f1x plus E of x, and we know that E of x is 0. Therefore, it is f1x is equal to 0, that is f1x, and hence f1 plus E is equal to f1. Similarly, we can show that E plus f1 is also equal to f1, and this is true for all f1 belongs to V. It means that there must be the identity denoted by E, which is a zero function, present in V. Similarly, if f1 is a continuous real valued function, then its minus f1 is also continuous real valued function, because due to the multiplication of minus 1 to any continuous function, that multiplication will not affect on the continuity of that function. Therefore, this is also belongs to V. This also belongs to V if f1 belongs to V. And if we add these two mappings, then I will get 0. 0 means it is an output of the identity mapping. So you can write this as E, and therefore sum of elements, two elements from V are giving identity. Therefore, minus f must be additive inverse of f1. So this is f1. Okay, so existence of inverse is also satisfied. And lastly, you can clearly say that commutative law always hold for the summation of continuous functions. Therefore, here also commutative law holds with respect to addition, and due to these 5 conditions, this V will become abelian group with respect to addition. And now the remaining conditions of the vector spaces, that is alpha into f1 plus f2 is equal to alpha f1 plus alpha f2, or you can write alpha plus beta of f1 is equal to alpha f1 plus beta f1, and 1 into f1 is equal to f1. And one more condition, that is what is the condition? Alpha into beta f1 is equal to alpha beta times f1. We can easily prove this, and therefore in this problem V is, that is a collection of real valued continuous function on unit interval, is vector space over the field F. Right. Now the next thing is, you keep this vector space in your mind, and now I'm writing something different. All right. In this example, let V be a vector space of all real valued continuous functions on unit interval 0 to 1. That means it is a vector space which we have discussed earlier. And here the collection denoted by W containing those elements from the V whose nth derivative exists. So V is a collection of mapping of real valued as well as continuous. We know that every differentiable function is continuous, but we cannot give any guarantee for continuous function is differentiable. But there are some functions which are continuous as well as whose nth derivative must be exist. Only those functions from the V we have collected, and that collection is denoted by W. And now we have to show that this W is a subspace of that vector space V. Okay. Now here I am writing clearly what is W. So today's guest is W, who want to become a subspace. So this W containing mappings which are real valued as well as which are continuous, and one more condition we have imposed on W, that is nth derivative of this mapping must be exist, and such a set want to become a subspace. So clearly here we can see all F from W are members of V. Therefore clearly there is no need to prove. Okay, so it is W is a subset of V. And now we have to check only the condition for the subspace. So for that we need two elements from the W. So let F and G belongs to W. It implies that, what is the condition? F and G, if they are members of W, it means that both F and G are real value functions, both are continuous on the closed interval 0 to 1, and their nth derivative exists. So I am writing here nth derivative of F and nth derivative of G must exist because they are members of W. Now I am considering two scalars, alpha, beta, and my claim is to show that this alpha F plus beta G is again a member of W. So how we can prove this? So since F is a real valued function, G is a real valued function, multiplication by any scalar to real valued function will not affect on its property of real valued function. Therefore alpha F and beta G both are real valued functions, and we know that sum of two real valued functions is again a real valued function. So we can say that alpha F plus beta G is a real valued function. Also it is continuous, real valued continuous function on unit interval. Now we have to check only last criteria, that is nth derivative of this must be exist, and if it will exist then this will become a member of W. So now I am finding nth derivative, that is the nth derivative operator. So this is, and now I want to find nth derivative of this quantity. We know that the differentiable operator is linear in nature. So linear in nature means we can write nth derivative of first term separately plus nth derivative of second term separately. Alright, now alpha we can take common from the differential operator, and therefore we can write this as alpha times nth derivative of F plus beta times nth derivative of G, and this is we can denote it by this notation. So here uh, nth derivative of f exists, nth derivative of g exists, therefore this is exists and this also exists, and therefore we can say that this summation must be exist, and therefore here this w is a subspace of vector space V. So after these examples, first of all, we have proved that intersection of two subspaces is again a subspace. What about the union of two subspaces? The union of two subspaces did not be a subspace of vector space V. It means that it may be subspace, it may not be subspace. We cannot say concretely. What happened when one subspace, or we can say the Cartesian product of two subspaces, is whether subspace or not? That we will see in our next video, and in that video, after proving the Cartesian product of two subspaces is again a subspace, after that we will discuss a new concept, that is the internal sum and external sum of vector spaces. So right now, give me permission. Bye bye.